Dear students, next we will look into Spe Taxonomy of computer programs. Here S stands for specified, P stands for problem, and E stands for evolving. You may recall the laws of software evolution. These were established by Beladi and Lehman by studying 20 releases of IBM OS 360. There are several of these laws, as you can see on the slides, while the first two are the most important. So the first one is the law of continuing change, which states that E-type program must be continually adapted, else they become progressively less satisfactory. And the second law of increasing complexity, which states that as an E-type program evolves, its complexity increases unless work is done to maintain or reduce it. So some of you might have already figured out that the laws of software evolution do not apply to all types of systems. And this was also discovered by Beladi and Lehman, and as they state in the laws, they only apply to E-type systems. So what are these E-type systems? Let's have a look. So we have the Spe taxonomy, which stands for specified, problem, and evolving. And the laws of the previous slide only apply to the E-type system or to the E-type programs. So what are these S-type systems then? An S-type system is a program for which all the non-functional and functional properties are formally and completely defined. As they are formally defined, they are defined outside of the real world, as you can see in the figure. Real world is here, and the formal statement of the problem is sort of outside of the real world. If a change occurs in the real world, it doesn't impact the specification of the program. Checking whether the program is acceptable for the stakeholders only consists of checking whether the solution produced by the program matches the formal definition of the program. Common S-type systems include programs that solve mathematical problems. For example, calculating the lowest common multiple of two integers or performing matrix operations such as addition, multiplication, or inversion. No matter what happens in the real world, these problems and their solutions won't change as they are formally defined. In the worst case, the problem is not relevant anymore to the stakeholders and a new problem is defined. In this case, the program doesn't evolve as it still satisfies the old problem. Instead, a new program solving the new problem is created. These types of systems are rare in the real world, but they can often be part of a larger E-type systems. Here is an example of S-type system. So we have a Python program package, sklinear linear model lasso. And what this program does, it basically follows the definition of lasso from this paper. So this paper is by Robert Tripshirivani. I hope I pronounced the name correctly. And it is titled Regression, Shrinkage and Selection via the Lasso. And in the paper, he gives a formal definition of this lasso procedure. And now what this program does, this sklinear model lasso, it just implements the formal specification provided in this mathematical paper that was published in 1996. Another example might be IP network definition. So RFC, which is the request for comments, that is how they standardize the network. And this is the exterior gateway protocol formal specification. So this would be perhaps another example of S-type program. Next, we have the P-type programs. P here stands for problem. P-type programs are different from S-type in the sense that their that in this case the problem is too complicated to be formally defined, and thus we need to rely on abstraction of the problem instead of complete specification. It should be noted that it's often difficult to make distinction between P-type and S-type programs. P-type programs give solutions to well-defined but not formal real-world problems. An example would be a program that tries to make money by trading stocks. Here, a change in the real world behavior of the stock market has impact on the problem. And this change might occur due to new and better computer trading algorithms. So if we assume that we have a program that trades stocks and makes money, here in this graph it would buy here on the top left, you can see my mouse. Then it would take profit in this point, meaning selling the stock. Here it would buy again from the bottom, and from the top it would sell again, and so on. So it is relatively easy to say whether this program makes money or not, and you can compare it to some of the stock market indexes, for example, and then you can figure out whether the program is any good or not. So it is a program that solves a problem, but this problem cannot be formally defined. And the difference here is that with S-type programs, if there would be a change, we would create a new and a different problem which would require a new solution. Here with P-type program, the problem is modified. In this case, it's the stock market, and the old solution needs to be adapted to fit the new definition of the problem. However, checking whether the solution satisfied the stakeholders is still the same. I mean, does the program make money in the stock market? And so you can see a clear difference here. If you think about, program that trades stocks and makes money, like tries to optimize buying and selling points over this graph, that is comes from the real world, versus a program that is defined already in some academic paper in mathematical terms, and then it's just implemented. So this is the S-type thing. And finally, we have E-type or evolving type programs. These are the ones that are fully embedded in the real world. Usually they mechanize a human or societal activity. They make some simplifying assumptions. They provide multiple interfaces with humans. They also have interfaces with other systems by requiring and providing interfaces through which they interact with other systems. And here it is impossible to provide any kind of formal specification to the problem. An important consideration is that subjectivity plays an important role for the acceptance of an E-type program, as it is entirely dependent upon the stakeholders' opinion and the judgment of the solution, whether the quality of the system is good or bad. These systems evolve through a feedback, as these opinions change over time, and because the outcome of the executing program is not entirely predictable. We can definitely state that Tudo system that you use for scheduling your studies is an E-type system. It evolves over time. People have different opinions on it. You cannot make a formal definition. And subjectivity determines whether this is a good system or a bad system. As the subjectivity plays a large role, people would have different opinions on the Tudo. And we can use this caricature for E-type systems. This is originally for software projects, but this works quite well as an illustration of E-type systems. So on the top left, where you can see my mouse, is how the customer explained it. So they wanted this type of swing with 3 ladders. And then we can jump on the top right and see how the business consultant described it. So this is what the business consultant thinks the customer needs. And finally, what the customer really needed was just a tire hanging on the rope from the tree. And in this in some way illustrates the subjectivity that is ongoing in the E-type system. What is not really captured here is how these opinions can change over time. So if the customer really needed this tire in the original phase, then 10 years later they might realize that, well, the business consultant was actually right. What we really need is this armchair on top of the swing. So all these laws of the software revolution only apply to these E-type systems. These P and S-type systems can be stated that they are rare, or it might be more correct to say that they are programs that are often part of the E-type system. For example, the P-type system that trades stocks and makes profit might be part of a banking application that would then be an E-type system. So these P and S are often nested in the E-type systems.